why does that do that, but that not? Why am I able to nail that into a wooden block, and yet I can't even nail it through my hand? The shape of it. If I was to press this in like this, that's great. But why is pressing it this way not a great idea? Well, it's because of pressure. You see, in all of these situations, I was bringing my force down to bear on a small area. With the scissors have got a point here where all of the force is acting. The area over which that force is acting is very small. And though the force involved is no more or less than the force of my fingers, because I've managed to concentrate that force to a really tiny area, it means the pressure is high. Same with the pin. The pin, if I apply a force that acts down on the really pointy end of the pin, it creates a large amount of pressure. If I apply a force the other way, to the large area end of the pin, it could never ever hurt me because the pressure is less. If I take a balloon and place it on a single pin, oh, it bursts. But if I take a balloon and place it on 100 pins, doesn't burst. And that's all because of pressure. With one pin, the force of me pressing this balloon is acting out on the one tiny little area of that one little pin. But here, it's having that force shared out between all of the various different pins. And so it doesn't burst the balloon. So why is this infinitely worse than this? The main reason is because of pressure. I have a larger area in contact with the floor. My weight is being spread out over that large area, meaning that the pressure at any one point on my body is much less. The relationship is as follows: that pressure is equal to force divided by area. Symbol P for pressure, measured in pascals, is equal to force, symbol capital F, measured in newtons, divided by the area, capital A, measured in meters squared. Now, what if that force acting down on the object was not me pressing down? What if it was the weight of, say, an object doing that pressing instead? Well, then that would still go here. So I have here a column of water and a balloon. I'm just going to trim the end of this balloon here like this. Try and do it neatly. Why can't I do it? I'm going to place the top of the balloon over here, a bit like a shower cap actually. Oh! And I'm going to use this hammer to press down, ram it right in. And I want you to observe what happens to the water coming out of this little hole at the bottom. When I apply more force at the top, what happens to the pressure acting on the water down below? So let's take a little look. Here we go, I'm going to apply pressure and here goes. Woo! Look at it go! When I apply more pressure, it squirts out further. Look how far. Look how far it goes. Oh. Yeah. But here's an unusual thing. why, when I pressed down, did the pressure make it come out sideways? Well, that's the only way that it could go. But this is one of the strange and interesting facts about fluidic pressure, or the pressure in a liquid, for example, or air pressure, is that because of the weight of, or the force acting down from above, it actually changes the air pressure, so it's acting in all directions. If I put another hole on this side, it would squirt out here too. And so, even though I'm pressing down, it actually causes the water to press out. So, this time no balloon, I'm afraid, but what I have done, I've filled it with water all the way to the top, and I have now got 3 holes, and I'm going to knock them all out all at the same time. It'll produce 3 jets, and they'll be different. Watch. 1, 2, 3. This one is under lower pressure than that one, which is under lower pressure than that one. And that is because there's less water above this hole. And so what's happened is there's less weight of water pressing down on the water to create the pressure of squirting it out. That means the deeper down you go in the ocean, for example, the more pressure you're under because of the weight of water above your head. But that weight of water is not felt on the top of your head, it's felt everywhere on your body as a kind of crushing force. It's the same in our atmosphere. Even though air feels relatively weightless, we are still here underneath about 100 kilometres of air, and that adds up, and it creates something that we know of as air pressure. This is a barometer. This actually measures air pressure, the amount of pressure that we can feel as a result of all of that air acting down on us and applying its weight to our bodies. Now, the reason why we see it on a wall is because air pressure gives us a clue about what the weather is about to do. And so for years, and before there were weather forecasts, we relied on a good old wall barometer to measure air pressure. Now, this is a digital jolly bulb on, and it measures air pressure in this little bulbous ball. And at the moment it's reading 97.2 kilopascals. Now kilo means 1000, so 97.3 actually means 97,300 pascals, which, give or take, is what the wall barometer also says. But now, watch what happens when I hold on to the bulbous end of this. A gentle cupping is needed. I hold on to this, and what you should now see is that the pressure is in fact going up. Isn't that bizarre? How am I, without getting inside this ball, able to affect the air pressure inside? It's because of my warm hands. Now I want you to imagine this. Now I'd like you to imagine this. This is a particle in a container, and it is hitting the walls and the ceiling and the floor of the container. Now every time it does so, it exerts a small force, and I can feel that, because as it hits the bat, I feel that force in my hand. Of course, it experiences a force back from the bat, and that's what changes its direction and makes it go the other way. But that ball hitting anything exerts a small force on that thing. Now, imagine this space filled up with several billion of those tennis balls, and they were all whacking around all over the place, including hitting the walls. It is that which causes pressure in the first place. You see, every time a molecule of air strikes my body and bounces off, it gives it a little push, and I feel that push spread out over my area, that force divided by my surface area is equal to the amount of pressure I am under from the atmosphere. So imagine this is a container, and this here is one of the particles within, just one of those billions and billions of air molecules. Now it's moving really rapidly, and what it's going to do is it's going to go and collide with the container wall and bounce off. In doing so, there is going to be some forces. First of all, the ball is going to exert a force into the wall. Now, anyone that's been hit by a football will tell you that they definitely feel a force from the ball. But also, there is an equal and opposite force acting on the ball which causes it to change direction. Now that force exerted on the wall, well, it's not just one particle doing this, it's many, and the force is being spread out over this whole area. And that force divided by the area will give you the amount of pressure from the equation before. Now, if we had a particle and it was moving faster, then when it collided with the walls of the container and bounced off, if it was travelling faster than the first one, then what we would find is then, like being kicked by a faster football, it's going to exert a greater force on the wall. So a much larger substantial force will be exerted on the wall, and the same back again to change the motion of such a fast-moving object. Now, because, as we discussed in the last video, the temperature of the object, of the particles, is connected to their motion, in that when the particles have more kinetic energy, they are vibrating more. Well, that is what causes the mercury in a thermometer to expand. What it means is that the temperature of a substance is linked to just how fast the particles are moving. And if they are moving fast, if the temperature is higher, then they're going to exert a greater force over that area, which means that this gas, if it was a hotter gas, is going to press the surface with much greater pressure than before. You cannot heat up a gas within a constant volume without having the pressure increase.